project which my mentor and I completed this summer at the US Naval Observatory, Flagstaff Station. So to begin with, solar system bodies are perturbed by various gravitational perturbations, including asteroids, other planets, general relativity, and solar oblateness. Spacecraft observations have led to high accuracy ephemeris, especially for the inner planets. However, there are still uncertainties of up to 1 kilometer in planetary positions. These uncertainties are largely caused by the asteroids. So previous work, Fienya and Simon in their 2005 research paper considered approximately 300 asteroids and their effects on planetary motion in the inner solar system. As well, they separately integrated the big 5 asteroids, Ceres, Pallas, Vesta, Iris, and Bacteria, separately from the planets so that they only feel these planets. So what they find is that asteroids, perturbations on Mercury and Venus are non-negligible. However, perturbations from the inner asteroids are quite negligible. Also, they find that the accuracy of the analytical model is comparable to the accuracy of high-precision numerical integrations. So in this project, our purpose is a little different. We are not trying to refine high-accuracy ephemeris, but more so to characterize generally the perturbative effects on planets due to the asteroids. So previous studies use approximately 300 asteroids. However, we believe that the asteroids can actually be separated into one of 3 groups. First off, the large asteroids. There are about a dozen or so of these. And these asteroids have an individual large effect on the planets. Second are the medium mass asteroids. These would be asteroids smaller than the large asteroids. However, their masses cannot be accurately modeled with a smooth mass distribution. So how to model these either as a mass ring or as discrete point masses is an interesting question which we will address. And thirdly are the small asteroids. There are hundreds of thousands of these asteroids, and they do not have any individual effect on the planets. However, there's a cumulative effect which perturbs the planets, possibly a non-negligible amount. So to analyze our result, we plan to use standard analysis tools such as Lyapunov exponents and power spectra. Lyapunov exponents will be used to gauge the amount of chaotic motion in the system, which will to some extent prevent the knowledge of planetary positions. Power spectra will be used to characterize the noise in the planetary motions due to the asteroids. So we hope to address some interesting questions with our study. Some of them are listed here. First off, because we will be measuring the perturbations on the planet due to the asteroids, we may be able to extrapolate asteroid masses from them, or at least place an upper and lower limit on their masses. Second, can we model the medium asteroid masses using an accurate way? This would either be as moving them on Keplerian orbits that are fixed, or as using fixed mass rings which would vary in mass density. Third, what is the significance of inner solar system asteroids? Now, Fienya and Simon in their paper have stated that they find that the inner solar system asteroids actually don't have a noticeable effect or a measurable effect on the planets. However, because our integration method is different from theirs, and as well we have a different approach to the problem, we may find that inner solar system asteroids actually do have an effect. Fourth, at what level does chaos prevent the knowledge of planetary positions? So this would be partially related to the Lyapunov exponents. And if chaos is present at a large degree, we would be unable to get accurate results of planetary positions. And finally, does the noise in the planetary motions resemble any of the standard types of noise? So the current state of the integrator is that it is functioning, and we've actually tested it by integrating the equations of motion for an earthbound projectile with air resistance. However, there appears to be a problem in the solar system equations of motion, leading to inaccurate results. So this is a screenshot of the integrator buoy, and you can see, for example, in the top left, that in the top left is Mercury's second major axis as a function of time, and you can see that its orbit stretches out after approximately 20 years to the orbit of Earth, and its orbit becomes parabolic, or near parabolic, and in that same point. So there's obviously a problem there, and once we get this fixed, we'll be able to continue to work on the project and to add in the asteroids.